Today we are starting chapter 2. And chapter 2 is much more serious than chapter 1. It is much more ambitious, actually, than chapter 1. And let's put a title, Introduction to Predicate Calculus. So how is this topic similar and how is it different from chapter 1? Let me write the following statement from chapter 1. P and Q implies R. Do you understand this propositional sentence, yes or no? Then what do we do about it? We can ask a couple of questions. Number one, is it tautology? Is it maybe true for all P, Q, and R? Is it contradiction? Or maybe if I give you particular valuation for P, Q, and R, do we know how to calculate if this the truth value of this statement? Yes or no? But here is what's happening. I don't discuss if P, Q, and R are true or false. Someone else needs to give me that. So if I look at the structure, it looks like this. P is here, 3 of that expression. Q is here, here is and, here is R, here is implies. So I will give you the truth value here on the bottom of the tree if you give me the values for the top. Do you agree? And I have no ambition to determine myself what's up there. And this is where logic is the base for the reasoning for any kind of science or any kind of rational human activity. But what happens today is we want P to give structure to P, Q, and R. And that means to make P, Q, and R be, for our examples, it will always be mathematical statements. They could be statements from economy, from physics, from whatever you do. So now P, I'll make a little balloon and give P a structure. And that's where predicate calculus comes. So, and now I will make some statements about mathematical objects. And then I will ask, is that true or not? But now it's not only about a table, it's about your knowledge of that discipline. So you need to know what these objects are, how they behave, and so on and so on. Do we understand that idea? But we have to be very careful when we make those statements. We have to do it in a way that's precise and understandable to everybody from our discipline. So what is it? Those statements can have fairly prescribed structure. And that's where what we do in this chapter is basically for you a little bit like learning foreign language. In this chapter, you need to learn how to say things in mathematics precisely. In a way where everybody else will understand you and where a machine will understand you. So let's say the following. For example, now comes the context. I want to make predicate calculus that will treat, for example, integers. So I want to talk something about integers. I'm doing integers, I'm studying integers. So generally you always first define the domain of your investigation. So domain. So here we'll have integers. Do we all know what integers are? So sometimes if you know it, no need to specify it. Or I will think of it as a world where who's there 0, -1, -2, 1, 2, 3, and so on. So that's our domain. And then objects from that domain are either specific or unspecified. So objects of our statements Here it is. 7. Do you understand what I mean here? We all imagine that there is an object there, and the name of that object is 7. Do we have unique way how we see that object, yes or no? For mathematical purposes, not philosophical. But sometimes I also want to talk about undisclosed objects. For them, we use variables. So sometimes I talk about the object x. And that object x is undisclosed. Do we do that in mathematics, yes or no? All right, so now we have names for objects, whether disclosed or undisclosed. What else? We usually say something about them. So there are properties. Or, more precisely, we call them predicates. Where every predicate has its length, and that is, how many objects are we discussing? For example, we'll say the following. We'll say the following. 6 is even. So I'm saying that number 6 has certain property. And what are you going to say? You'll say yes or no. Do you agree? So properties always have answer true, false. And how do we determine that? That's not topic of our discussion. That's more intrinsic discipline. For logic, you need, so is this a property, yes or no? Yeah. And it's property of how many numbers? Just one number? I mean, am I talking about particular number, 6? Or what else? Can I say x is even? Can I say that as well? Yes, but then what happens? When I keep changing x, the truth will change from true to false and back, agree? Those are called basic sentences. Or what else? Can I say the following? X plus 1 equals to 7. Is this also a property, yes or no? Yes, it is. That's a property expressed using operations and everything. Again, so property, you always say, how many inputs do I need to feed, if any? And then, can I always say yes or no? So is this a property, 5 plus 3? Is this a property or not? No, this is operation. For this one, everybody expects me to feed answer or simplification or something like that. So that's not a property, but this is a property. If you feed the value for x, if you specify a variable, it will say yes or no, agree? What else? So these are all properties. Usually for all of them, I'll just call them R of x. So that's property of R of x, it's x is even. And then 6 is even is basically R of 6. And let's say 6 has property R. So you always describe a property. Is that clear to everybody? What about this? X greater than y. Does it make sense to call this property yes or no? Can you answer this yes or no? Yeah. But in order to do that, I need to give you how many numbers? 2 numbers. So this is also a predicate, but with how many variables? 2 variables, or we say very often arity2, because it's binary. So it's binary arity2, or we just say binary predicate. We'll talk more about predicates in chapter 6, but this is just something that we need in order to be able to talk. So you always use predicates to talk about your objects. So we have objects, we have predicates. And now predicates are connected using logical symbols. So for example, I'll say the following. Here's one more predicate. I just want to introduce it. And this is divides. So what is the predicate divide? X divides into y. So this is again binary predicate. So for example, what if I say, does 2 divide into 6, yes or no? It's not divisible, it divides into. So does 2 divide into 6? Yes. So the answer is yes. Does 5 divide into 6? No. So let me make one statement that we already had before. 2 divides into 6. 3 divide into 6. 5 divides into 6. This is now mathematics. Yes?
Divides into, you mean the second number is still 11?
Divisible by first one, yes. But we always use this relation, and that's how it is. You need to get adjusted to it, to read it from smaller to bigger, okay? So, or you would say exactly, x divides into y, we also say y is divisible by x. And then what? So for example, what happened here?
How is that? You're saying it doesn't divide, is that because you're saying the domain is integers? 5 doesn't divide into 6 because it's integers?
Because you cannot divide 6 by 5 evenly.
Okay.
It has a remainder.
Or that condition is because you said the domain is integers.
Oh yes, yeah. Oh yeah. I understand. It's not like 1.2 quotient or something like that. True. This is all on integers. You're right. So now what happens? Now my idea is not give me values for P, Q, and R. Now with my knowledge of mathematics or knowledge of the domain, I can decide on my own if that's true or false. Do you agree? So what happens? 2 divides into 6. What's that? True. 3 divides into 6 is what? True. 5 divides into 6 is what? False. So this is true. True implies false. And that's how you make statements about objects in mathematics, and that's how we check if they are true or false, and that's how we express our knowledge about the objects. Is that clear to everybody? All right. So what happened here? These are specific objects. So here I really made the statements about very specific numbers. I didn't give any undisclosed objects or any variables there. Let me change story a little bit. By the way, we call this a sentence because there are no open variables. Let me now change this the following way. 2 divides n. Usually it's x or n, a variable. 3 divides n. 6 divides n. What happens with this statement? Is it true or false? Oh, there's a variable, so it depends, do you agree? So let me see, what can I feed there? What if I feed there 12? Will that statement be true? Why? Because this is true, this is true, this is true. You calculate and you get true. Everybody okay with that? What if I feed n to be 11? It's also true. Why? Because this is false, this is false. False imply anything is true. You get true. Can anyone think of any number n that I can feed and get a false statement? No. When that happens, then we express that fact the following way with something called, so generally we don't always write trees. Unfortunately, it would be very nice for mathematics and for this realization if instead of writing one-line formula, we write those trees, because then PEMDAS and all those rules would never be an issue. Kids would be much better in mathematics. So, but unfortunately, we do write in one line. And then let me write a statement that we have here. So we'll say the following. 2 divides n, and 3 divides n, implies 6 divides n. This is a statement. These statements has, we say, one alive variable. Why is this variable? And this is the main thing to learn today. This statement has one free or alive variable. Why? When I write it like this, I cannot start it. I'm waiting for you. And you need to tell me what, how much is n, and then I'll start calculating. Ready? And that's called n is free variable. Why? Because I don't know what it is. But now, and that's what's new here, we noticed a minute ago that this statement was true. I don't need to wait for you to tell me n, because I know whatever you give me, the answer will be true. Do you agree? And I'll make the following statement. That this, what I just had, is true for every n. And this is the new thing. We say universal quantifier, every, which is like a backwards, upside down, for every n. This is what we call a universal statement. So that's a new thing. So sometimes in the structure, what I did here, when I had everything built, I also attached a universal quantifier. At the end, I build everything, and at the end, I also have a universal quantifier. When this and this is a world of a difference. Why? Although they tell me the same thing, but generally, when I write it like this, I wait for you to give me n. Do you agree? What about here? I don't wait for you. Why? Because this statement is either true or false. Because what? And that's actually one of the main things to learn today. How do you check the truth value of universal quantifier? You don't wait for anyone to give you n. You start plugging all n's. And then what happens? If you always get true, you will say, yes, the universal statement is true. First time when I run into false, I stop and I say, what? The whole thing is false. So this is just, doesn't have true, it's just true or false. It's not like for some n's true, for some n's false. I made the commitment to say that it's true for all n's. So either it is true for all n's, and I'm true, or it's not, and you will give me something called counterexample, and that's false. Does that make sense to everybody? This variable, is there an n here in my expression, yes or no? But that n is not free anymore. Why? Did I wait for you, or I was plugging it on my own? Plugging on my own, and this is when we say that the variable is bound. And that's a huge difference. You have to pay attention. Only if you have free variables, you need to feed them and to wait for the feed and say, oh, if I feed it this way, it might be true. When you have universal statement like this one or existential, then just that means you feed on your own and make a result without waiting for the value. And that's important thing for the for predicate calculus. What else? So basically, this is how the statements look like, and it's a couple of warnings. We need to practice a lot on this. But you will see homework will be somewhat frustrating because it will be really like talking foreign language. But it is important how parentheses work. So for example, when I build my statement, I finished everything, and then I did universal quantifier. Sometimes I do universal quantifier only on antecedents, and things change completely. So you have to be very careful with the way how you build expressions. And that, in section 2, we need to learn some technical details. It's simpler. But this is very important that you understand how to say things precisely in mathematics and express and introduce language and objects the way you need them. Before we take a break, I know this hour came to be a little longer. It might help you to see the difference between free and bound variable if you see something like this. Let's say f of I, usually, is I plus 4. Can you calculate this? If before someone gives you I, can you calculate it? No, that's a live variable. Free variable I, that just needs a value in order to execute. But look at this. S of I is sum of I plus 4 when I goes from 1 to 7. What about this? Will I get function or I'll get a number at the end? I get a number. I don't need to wait for anyone to give me value for I. I will keep plugging 5 plus 6 plus 11. I'll add them up. And whatever that number is, by the way, it's what? 16 times 8, 56, I think. You will add them up, and I'll get 56 at the end. Then look at the difference. Here I get a number. Do you see any traces of that I? No, that's what bound variable is. You kind of use it, but it disappears. It's just your kind of tool. But here, it stays in the result, and without, if you don't give it a value, you're not going to be able to accomplish it. The same thing with integral. How much is integral of x dx? X squared over 2 plus c. Okay, forget that plus c for a moment. What? Now, can I calculate this, or I want from you to give me value for x? I'm not going to get number unless you tell me how much is x. Do you agree? So indefinite integral is a function. What about definite integral? You say x squared over 2 between 3 and 7. Do I wait for you, or I keep calculating? Yeah, so I'll get whatever it is, 40 over 2, which is 20 probably. So I'll get a number, and that's it. So what? This variable here in indefinite integral is a free variable, or alive. What about this one? It's bound variable. That means doesn't appear in the result. The same here, the same here. So whenever it kind of looks too abstract, connect with the examples that you are familiar with, and I hope it will sound better. Yes?
How would we treat it if the sum had bound of infinity on the top?
That's more complicated. Then there is a limit there. That's what it is. So sum infinity means there is a limit on those sums. So that's now calculus. This is just pure algebra, and then you need combination of those. But at the end you will get a number as well. But that number will be not one sum, tons of sums and their trend. So that's another complexity. It's worth discussing, but it will make story more. I would rather stay with simple than, because this is just to illustrate what's going on. So, but it's a very legitimate one. So generally here it is. If I go like, but what if I go like this? Sum of 1 goes 1 to k I plus 4. Do I get a number, or I get a function? Of what? Of I or of k? So this is function of k. This is still a bound variable, but k. What about second fundamental theorem of calculus? If you have integral of t plus 1 dt from 1 to x, who's your variable? X. And when you make derivative of that function of x, who do you get? Do you get function of t or function of x? How do you get it? Plug in x, and you get what? X plus 1. Hopefully fundamental theorem of calculus now makes more sense. So who's your free variable here? Not t. Who is it? That's why our derivative is function of x and not of t. So those are a couple of places where that big idea in mathematics of bound and free variable. So generally, first thing, when you see a sentence in predicate calculus, you say, who are all my variables? Which of them are free? Which ones are bound? Is that clear? And then what? Oh, and one more comment, and then we'll really take a break. If you look at this, is x bound or free variable? Yes, there are two appearances. You see, this x is under the action of quantifier. See that quantifier only acts on this x. Do you see that? What about this one? No. So this one is bound, and this one is what? Free. So this is quite confusing. You know what I would do then? Bound said run it through, so I would rename this one and call it z. You always can rename bound variable. If I say I goes from 1 to 7, can I call it j and run it from 1 to 7 again, yes or no? So bound variable you can always change, free variable you cannot. So generally here, now z is bound and x what? X is free. By the way, you can also see that from the tree. Here it is, Z greater than 3. Then there is a quantifier, X less than 7. There is and that's what it is. This influences this, doesn't influence this because this came into 3 after that universal quantifier. Universal quantifier only acts on the subformula that it covers. I know it's still a lot. I know it all looks like what's going on here. You know, you need just to play. You will see in the homework. We'll try to record sentences. So we want to learn those basic techniques, how to establish things. One of the biggest problems is I started with integers because it's easy. We are all familiar with it, so it was clear what your domain is. Sometimes you need to make domain the way you kind of like it, the way it will help you to express yourself. So you're kind of making the world, you know. I say, all right, I'll start my world in order to express myself. I say, here are the objects that I want to analyze. Here are their names. Here are the relations I want to study. So you introduce all of them like you are introducing them when you make some computer language or something. So introduce alphabet that you want to work with, and then you start making statements and checking if they are true or false. So that's how the whole mechanism works, but it will take us a while to become familiar with it. Let's take a break finally. So we continue 2:45.